Good afternoon. Thank you for joining us for today's Tech Talk as part of our knowledge learning programme. Today's Tech Talk is about service risers and penetrations. I'm Steve Musa, one of the project team, and I'm joined by our technical director, Jayesh. Good afternoon, Jayesh.
Good afternoon, everyone.
So we're going to look at service risers and penetrations. So the first question, Jay, why use carbon fibre?
Yeah, so carbon fiber strengthening becoming quite popular nowadays, purely because it is very high strength and lightweight material. It can be used for strengthening concrete structures, steel, wrought iron, cast iron, even on timber structures. Just to give a feel in terms of number, carbon fiber is at least 3 to 4 times stronger than steel and at least 7 to 8 times lighter than steel. So you could see this strength to weight ratio and why people use FRP over traditional methods, and that's the reason that it is quite commonly used these days.
And a lot of people think it's sort of a new technology, it's only just recently come, and that's not the case, yeah?
No, it's not a new technology. This was used in 1940s in aerospace engineering. Then they started making all the aeroplanes, fiber boats, motor cars using FRP. And then in late 1980s, this was first used in construction for strengthening of bridge structures to protect them from collapsing due to earthquake.
Mm-hmm.
So that's how it actually came into industry. But the reason why we think it's a new, because as compared to steel and concrete,
mm-hmm.
it is still new technology, but not entirely new. So we have more than 32 years of case study available in UK itself. The first project was done in 1992.
And we're seeing a lot more sort of main contractors and general contractors going to designers, asking them, can we use a carbon fibre solution? And it's not just for the strengthening side?
Yes, because it is a very economic solution if you see the whole cost in terms of material, labor, disruption to the structure, and most importantly, time in doing that strengthening. You saved a lot of time. So from contractor's point of view, if you're able to reduce your program time, you'll be able to save, prelims and everything. So from that point of view, it becomes a very economical solution. But they have to see the whole cost. You can't just compare just the cost of material of carbon fiber with cost of concrete or steel. If you do that way, you may find it expensive. But if you see the whole cost, then this is the most economical solution available in the industry at the moment.
Okay. So we're here to talk about the service risers and penetration side, because we're seeing a lot of this on building work now, where they've got to put in a lot of M&E works, yeah?
Yes, so this is another type of service of strengthening which can easily be done using carbon fiber strengthening systems.
Yeah.
So this is quite common requirement, especially when you're refurbishing an existing structure or changing the use of an existing structure. For example, a commercial building converted into a hotel,
okay.
or maybe in a school or something. They may have to have new openings through existing reinforced concrete elements.
So that's the picture on the far left, then what's that showing us?
So that's a door opening through a shear core. So this is another refurbishment scheme where we worked in London, and they were refurbishing the structure, adding additional stories on top of it,
mm-hmm.
and they needed additional door openings through shear core for new lifts. So that was done using carbon fiber.
And the picture in the center?
Yeah, that is an example from Premier Inn Hotel in Kingston upon Thames. So this was an existing commercial building bought by a Premier Inn Hotel. And they were cutting these kind of, creating these kind of penetrations through reinforced concrete flat slab mm-hmm. in every ensuite bathroom location. And there were 180 bedrooms in
wow.
that hotel. So if they do this kind of solution, if they use traditional method of using traditional steel, they'll end up using a lot of steel, which could add a lot of weight and also mainly the time.
Yeah.
So it is done using carbon fiber strengthening system. So it's same sort of trimming, but that is done using FRP.
And the process of the behind when you're looking to use that system in the middle?
Yes, so it's basically you work on the same principles of trimming here, but again, because when you cut these kind of cores, you will cut some rebars in the slab. Those rebars will generate additional forces in the surrounding area, and you design FRP for those additional tensile forces. So that's a very straightforward design principle on that.
Mm-hmm.
But if there are bigger openings, as you could see in the leftmost or rightmost images,
mm-hmm.
Then in that instance, we usually recommend the project engineer should do a finite element analysis and model
okay.
this structure before and after, and then see the actual tensile stresses and design FRP for those stresses rather than working on force equivalency.
So we're going to look at the general design principles now for using carbon fibre in this area.
Yeah, so as I said that the design principles are two approaches we can take, as we have already discussed. One is based on force equivalency, where you design FRP based on the number of rebars you are going to cut in that opening. But if the openings are bigger, then technically it should be designed based on the forces generated after the opening is formed in an FE model or something. But again, once we know that force, how to design FRP for that force. So this is a typical stress strain behavior of FRP compared with steel, which shows the difference between the steel design and carbon design. So mainly we could see that the black curve, which shows the behavior of steel, we design it on the yield stress and everything. The top green line shows behavior of carbon fiber. Bottom green line shows behavior of glass fiber, which shows that glass fiber is more ductile, in other words, or it could deform a lot more as compared to the traditional steel. Carbon fiber is stronger than steel, so that's why it is used most commonly for pure strengthening works. But the most important thing we could see on this stress strain distribution curve is that both carbon fiber or glass fiber has a linear elastic behavior until their ultimate load or ultimate stress, which means that there is no yield point or warning in FRP before failure. So the ultimate failure in the FRP is brittle in nature. So to avoid that failure, FRP design is always a strain limit design.
Okay.
So how we design the FRP is basically we take the modulus of material and the thickness of material from the data sheet, and then we derive the strain value depending on the guideline we are following, type of strengthening we are doing, and then multiply that modulus with the derived strain. That will give us a design stress for FRP for that particular requirement for that particular area. That stress should be used to calculate the area of FRP for a particular force.
So that's a critical point.
It is a very, very important point for designers, that FRP design will always be a strain limit design. It should never be designed based on the tensile stresses given on the data sheet.
So when you look into when you look at dry properties, and when you actually look into dry versus cured.
So FRP is a composite material. So you have at least two materials mixed together to make FRP. So you have a dry fiber that is mixed with epoxy matrix. When it cures, it becomes a laminate. That laminate is called FRP. So we could see on this stress strain behavior, the blue line shows the behavior of just the fiber only, which shows very high strength and low strain values and everything. And then we have the epoxy matrix property as well in purple. And then when they are mixed together, then the behavior of carbon fiber or FRP will come. That is called the composite laminate property. So FRP should always be designed based on this final cured laminate property, and not just the dry fiber, which is a common mistake made in the past by the designers.
Okay. So we're going to look at some project examples now. I think there's a project we did quite recently in Birmingham.
So this is for service riser penetration through the beams, which is, again, as I said, it's quite common these days, especially when you are reusing, or as we call it, adaptive reuse of an existing structure. So in this instance, they wanted to put new services through the floor plate, and though the best place to put those services was through the beam, so that they could remain very close to the slab and they don't lose any headroom from existing structure, because it was anyways not a very high headroom. It was hardly 3 meters from slab to slab. So that's why they decided to go through the beams. So they needed new penetrations through the beam, and that's why the strengthening was required.
So the site conditions, obviously, for perfect weather in the summer and that, but we have to do various checks before we can look to apply carbon fibre,
So the carbon fiber is applied in a certain, environmental and climatic conditions. You need minimum 4 degrees centigrade temperature to apply FRP. Humidity should be less than 85% and all. So as you said, that in the winter months, it's very difficult to get those kind of, weather naturally. So you have to create these kind of artificial, environment and enclosure and everything, where you put the heaters on, raise the temperature if required.
So that's shown in the picture on the left and in the centre, where we're raising the temperature of the immediate area. And the picture on the far right, what the guy there is.
That's a quality control process, where they have to take the temperature readings before applying the carbon fiber, so that there is a record kept for every application, in which environment it was applied, so that it can be referred back to if required, and we can have a full control over application.
So we're going to see the video of the application process itself, yeah?
Yeah, so first thing is surface preparation, which is done by diamond grinding. So usually the plaster was removed by the main contractor, then we drill a hole through the anchors for carbon fiber into the beam and slab junction so that we have a continuity there. Then they grind the area, clean the area, so it needs to be dust free.
Yeah.
And then once that's been done, then they can continue with the application. So before doing the application, they will take the temperature readings again to make sure that the temperature is still as it needs to be after putting the heating there in this particular instance. After that, they'll do priming, which is done using pure epoxy, so it can soak into concrete. Then they unroll provide the first coat of thickened epoxy, which is the white color epoxy we are seeing. And then once that coat is applied, after that they will unroll the first layer of carbon fiber, which is saturated on the site in a different area. So when they are applying it, it's in wet condition. So when they applied the first layer, then they will apply the second coat of epoxy, followed on by, if there is any anchor installation, they will put the anchors in, otherwise put the next coat of next layer of carbon fiber. But in this instance, because it's a shear strengthening, we use the carbon fiber anchors so that we have a full detailing there, like in a closed loop. So that's why the anchors were installed in. So they'll put the anchor into the drilled hole, which is filled with epoxy. Then they splay the anchor onto already laid layer, and then put another layer. So the anchor will be sandwiched between two layers, or if it is a last layer application, multiple layer, then it will be just put in just before the last layer. So it will always be sandwiched between the layers.
Yeah.
So once that's done, then they apply the final coat of epoxy and take out any air bubbles from it. So that's how ultimately the application is done. But again, as I said, it's saturated prior to application, so the application is called wet layup method.
So once the process is complete, how long is it then before the contractor can come back and actually core drill the beam?
Yeah, so in ambient condition, the FRP will be 100% cured in 72 hours. So they can come back in 3 to 4 days time and core this opening. The reason for doing this strengthening prior to coring is that right now there is no damage to the existing reinforcement and everything, so FRP could remain as it is. But as soon as they core it and cut a rebar, the FRP will be stressed, so that any additional stresses will go into the FRP, so that you utilize the FRP completely in that way. So here are some images we could see. So this is before and after strengthening. So first we did this strengthening as we've seen in the video.
Yeah.
Then after the curing, the contractor came and cored through the beam.
So when we've sort of finally done the test, and we need to, as part of our QA/QC procedures, we have two tests that we look at.
Yeah, so because it's a bond critical application where we are relying on bond between FRP and concrete, we do a pull-off test, which is the test all the project engineers should ask contractor to do if there is a bond critical application, which could be a beam strengthening, slab strengthening, wall strengthening. So in the bond test, all we want to make sure is that FRP is bonded correctly onto the substrate, which shows that the preparation was correct, the saturation was correct, the installation was correct. So the difference between this pull-off test, which we do for FRP strengthening, and the standard concrete pull-off test is that in concrete test we look out for a number in terms of pull-out strength, that whether it's what value it is, 2 MPa, 3 MPa, depending on grade of concrete. But in FRP pull-off test, we are more interested in mode of failure. So what we do is that we put a sacrificial patch on the same structure which we are strengthening.
So that's what's shown on the left-hand side, yeah?
Yeah, it is. So in this particular instance, it was a beam flexural strengthening, but we put a patch on the side of it, so it can cure in the same environment.
Yeah.
After the 100% curing, which as I said is 72 hours, we perform the pull-off test. So all we want to see is that when you do this pull-off test, it should not come off from substrate only, or should not come out from another layer of FRP if there are multiple layers. So in the middle image, we could see that when they pulled it off, it took out some concrete with it, which shows that the bond between FRP and concrete is stronger than the actual concrete failure strength. So that's the pass criteria for bond test. And then the second test we do is basically to check the property of material. So this is called plate testing, and it tested the composite property. So it is mixed together. So when they do the saturation of the fabric, they also create these 300 millimeter by 300 millimeter wide plates, The current requirement as per TR55 is to cast 2 plates per day or 2 plates per roll of the fiber, whichever is higher. And they send it to an independent laboratory. They'll cast a coupon out of it and do a tensile test. Those tensile properties should match with the data sheet of the material or should match with the design values which you've used in your design. So that's the pass criteria. It will tell you what sort of material has been applied onto the structure, and that's why I say that in the design we should always consider the final cured laminate property, because you can directly compare these test results with your design values.
And for quality assurance purposes, the test places are kept on site in our works?
Yeah, they will be left on site to cure, but once they are cured, we'll keep them in our record, and if required, client can have a sample as well for their future references if needed.
Okay. Okay, well that's our tech talk for today. Thank you for joining us. If you'd like more information, if you go to the website, there's quite a lot of information that you can look at, our YouTube channel also. Well, thank you for joining us today. If you'd like a certificate, please scan the QR code which is shown on the screen now. Thanks for joining us. Hope to be working with you soon. Goodbye.
Thank you.